So, hello everybody. It's my great pleasure to introduce you Eduard Eiben. He is from Royal Holloway University of London. He's visiting together with Argyrios and Tiger this week, our group. Feel free to reach them, and Eduard will speak about parameterized complexity of coordinated motion planning. Eduard, stage is yours.
Thank you very much for introduction. And hello, everyone. I'll tell you a little bit about parameterized complexity of coordinated motion planning, or some people call it multi-agent pathfinding. And I think some people in here also work on related things, at least Dushan and Fibas, and maybe some more. And yes, so that people. So they will also be able to answer some of the questions, maybe not about results I mentioned here, but about others. So I will mostly tell you something about our first result on this, which was with just Robert and Ian. But I will mention also some follow-up results with also Argyris that is here and Ramanujan. So let us start a little bit with motivation, in case not, even though you have people working on it, maybe not everyone is kind of familiar with the problem. So basically, motivation is you have say a large warehouse or where you need to automate navigating some items from one place to another, right? So you have Amazon has a huge warehouses where they need to just pick up some items and bring them somewhere else, and then pick up some items and bring them somewhere else, and they need to do it for lots of items. And for that, they acquired in 2012 Kiva robots, exactly to just move things around the warehouse. And robots just have to move some items from their starting point to some target location, right? And they can move simultaneously, right? So how it looks, at least how it looked a couple of years ago in Amazon warehouses, it's you have these small robots and they move stacks of things from one place to another, and they are moving at the same time, and ideally they are not colliding with each other and anything like that. Okay, so this is kind of for motivation. Of course, at least myself and many people here are more theoretical computer scientists. So we have at least some nice motivation, but now we should introduce some theoretical problem for which we have some theoretical results. So we have some robots, and now our first results that I will also speak about was on the grid, and also which kind of makes sense with Amazon warehouses. But in general, we can generalize it that we have a graph, and we have some number k of robots on a graph, and all robots are starting at some positions, and some of them, say for simplicity, all robots have also some destination which they need to reach. And now in each step, we are on the graph. So in each step, a robot can move to a neighboring vertex on the graph, or it can stay at its position. So it's not like just path. So it can stop. It can not move if it doesn't need to. But what we want to avoid collisions, right? So the motivation is still kind of a robot in a warehouse, and it would be quite bad if they were colliding all the time with each other, because they cannot actually pass through the same position at the same time. And what we want to do is we want to find the schedule for all the robots to achieve their objective, to reach their destination, while we want to minimize some objective. And two very prominent objective in this for this problem are schedule length, so number of time steps that we need to finalize, such that every robot is at the destination in the last time step, or kind of a total travel length, in which some people call total energy, because you can think about it as a robot needs a different amount of energy to just stay idle at a place or move to a neighbor, right? So if we want want to minimize the total amount of energy that all robots use together, we get this other optimization target. And there are some others, but we mostly work with these two, and there are a few more that people looked at as well. Okay, so how it looks in a simplified grid version and what we want, right? So we start with a robot at their starting position like that, and they want to get to their destination. So, for example, this red robot here wants to reach this square here. This orange wants to go down and reach this square. Blue wants to go to the left, and so on. So how we can do it? We can do something like this. And now notice that at this time, this red robot here stopped and waited one move for green to go down. And as you can kind of imagine, we don't necessarily consider collision if a robot is moving to a place where another robot was step before, right? Like here. Right? And we kind of can see that this schedule that we had here is actually also optimal for both of these objectives, because first, for example, green robot is moving in every time step. So green robot is going on the shortest path and moving every time step. And all of the robots actually walk on the shortest path, with only red waiting one step. Okay. So is the problem clear? What we are considering? Yes, good. Right. So this is actually a relatively very well studied problem. So people started studying it already in 80s. It was also related to, they studied it as some pebble reconfigurations, but also a lot of they were studying it from computational geometry point of view, where robots only move somewhere on the plane. Also, a lot of people studied in AI and robotics. So now there are lots of papers about this. There are there have been quite a few workshop at AAA and ICHCAI related to this. I'm not sure whether there are still there was something in last year or two, but 2 years ago when I created the slide, there have been several years in a row workshop related to this multi-agent pathfinding. In Solstice 2021, it was they had exactly this problem, and even just on the grid as a computational challenge. And there are many algorithms, many heuristics, some websites, benchmarks, and so on dedicated to MAPF or CMP. This problem. And as you can imagine, there are also many kind of variants and settings. So people consider it on graphs, people consider it on grids, on subgrids, so grids with some obstacles. People consider it in geometric setting, where it's on plane. Again, either there are some obstacles or there is some bounding a box or not, and things like that. And also, people consider different conflict notions. So in some cases, it's allowed to use the same edge at the same time, just not being at the same vertex at the same time, which is like the robots are moving some packages and they're allowed to exchange the package, so they can move along, which is the same as kind of moving at the same time along the same edge in opposite direction. So they exchange the item. Sometimes you can consider, for example, when people think about it as some drones, they only consider they have some starting time, so they don't necessarily need to start at the beginning, and they can disappear at the end, because they're only kind of measured when they are in the air, and they are doing something when these drones are in the air, and when they're on the ground, they can collide with some other drone, can just fly about. You know the problem. And sometimes you care exactly, like in our setting that we will discuss, where every robot has exact destination, and single destination, but you can maybe have just set of k destinations and say the robots need to be one on each of these. And you can split robots into some color classes where you have different label for each robot and different label for each destination, and you just need robots to reach the destination of the same label and things like that. And most of these settings are very hard, and they're very hard even on instances like grids or trees. So if you want to know how hard it is on trees, you can ask Dushan. I will actually, all the results that I will mention are algorithmic and not no hardness, but even though we had some hardness results as well. Okay, just something that we will need from parameterized complexity. Probably many of you are familiar with parameterized complexity, but main thing that is kind of a holy grail of parameterized complexity, what it means to be tractable is fixed parameter tractability, where we have an algorithm which runs in time some function of this parameter times polynomial. So you have the same for every value of the parameter. If we consider it as a constant, there's the same polynomial running time. And para-NP hard means it's hard for some constant value of a parameter. And I didn't mention here, and might mention later, W hardness, which is like its assumption, like working assumption of parameterized complexity is that if something is W1 hard, then it doesn't have an FPT algorithm. So FPT not equal W1, or is like a working hypothesis of parameterized complexity. Okay, so back to our problem, and back to maybe some definitions. So again, we have a graph. We have this set of robots. We'll be referring to robots quite often as R with some index. If we need to, we assume each has some starting point, each has some destination. So starting point S, destination T. And now a route for some robot would be like a walk. So exactly his movement throughout the execution of the schedule. So it will be like a walk which allows to stop at some point. Right? So it's a sequence of vertices, and some like consecutive vertices are either the same vertex or adjacent by an edge. And a conflict is if two robots are either the same vertex or they take the same edge in opposite direction, right? So we cannot have a schedule telling two robots to go to the same vertex at the same time, and we cannot have a schedule telling robots to go in opposite direction along the same edge. Okay, and then the schedule is just a set of routes for all robots that are non-conflicting. And just the makespan is the completion time. So if the time interval for the schedule is st, then makespan is t. So if our schedule finishes at time t, then makespan of the schedule is t. Okay, and the first question that we would like to answer, and where I will now tell you two algorithms for two different versions, is there a schedule for robot of makespan at most L? Just I will give you some FPT results for that, just to mention. It's even on grids, it's NP hard for constant L. So if we don't bound the number of robots, just L, even from constant L, even on grid, it's hard. For grids, it's something like L26. For bounded degree graphs, which again you can ask Dushan, is hard even for like L equal 3 NP hard. But we will look at the grids and we will do a 2, even 2. Okay. No, sorry to yeah. It's NP hard even for value 2 on bounded degree graphs. Okay, so now I will tell you something about FPT algorithm on grids, and of course we'll not parameterize by L, but by K, by number of robots. So how the proof on the grids look like? We start by actually showing that there exists some kind of a canonical solution. This canonical solution will be just each robot will be making small number of turns. We are on the grid, and we will just so it's easy to think about what a turn is on grid. And once we know that there exists a solution and a small number of turns, we will just use IOP to actually find such solution. With IOP with a function of k-many variables. So we can use one struct, for example. Okay, so a turn on the grid, right? So we have a grid. So a turn is just robot have been moving this direction, then it changes direction either to up, to down, or even to back. So we even consider turn changing direction by 180 degrees, right? And we say that a schedule is turn minimal if the number of turns made by this route is minimal. Probably turn minimum, it might be a better term, but yeah, let's say it's not that important right now. And what we want to now show is that if we have a schedule that is turn minimal, or that where we cannot get smaller number of turns than in that schedule, then the number of turns there is bounded. And there are kind of two kind of turns that the robot will be doing. So one thing is robot is just really going towards its destination, around kind of up the stairs, but it's turning a lot. And one is it can be also moving like around, going back and forth somewhere. So let's first consider the first part.
Can the robot just stop and not move?
Yeah, robot can also stop. Let's it's not so we will bound both things. So we will bound also the number of stops. So we first bound really number of turns, and then once we know that that number of turns is bounded, then there are only few kind of reasonable positions where you can assume that the robot is stopping. So we will bound both, but we will start by bounding the one where we just assume they are kind of going and just changing directions. And then once we have bound and changed direction, we will not say it today, but there you can kind of see that you can bound the number of places, because we need, for IOP, we need bounded both. Yeah, and we have bounded both, right? So, but we will start now with trying to get rid of these kind of stairs. So we will have kind of sequence of monotone sequence of turns, which is always going kind of just two directions. Just, for example, right up, right up, right up, right up, right? So it will be a monotone sequence of turns. And what we would like to do with such monotone sequence of turns is to do some operation like this, kind of flatten it. So if you have a turn like this, we would like to change it to this one. And the reason why we might not be able to do it is just that if we do that, there would be collision somewhere, right? So there is some robot moving something like this, and if we just flatten it like this, they might collide. In here, okay. So to show that we actually, in many situations, we can actually do it, we will also need to introduce one other notion, which is a notion of a slack. And slack is kind of a notion of how much a robot is slacking on some interval. So we have some time interval, and we have some 2 points. Actually, let's look at the definition. So we have time interval and 2 points. And we look at the distance of these 2 points, and the difference between the distance and the time that particular robot used to reach there. So I forgot to say it on the like 2 slides ago, but so from now on, what we are doing is we are assuming we have a turn minimal solution, and we are trying to show that that solution has small number of turns. So right now we are assuming that we have routes for all the robots, and we are analyzing the routes of the robots. So right now we are assuming we have a solution in hand. So saying something like, take a particular robot, look at some sub-interval of that robot. It's okay because we know the routes of all the robots, because we are right now analyzing, just trying to claim that turn minimal solution has bounded number of turns. So we have a solution in hand. We don't have to know how to compute it or anything. We just are analyzing it. So we have some solution in hand. We look at some robot, and we look at some 2 points and some time interval, and we look what's the difference between the distance and how much time actually robot spent to reach these two, right? Which kind of means that if the slag is large, it means that robot could have stayed somewhere. Robot was allowed to go like back and forth, and it even could actually reach that final destination and just stay there for a long time. It's all of this is fine, but it has a lot of freedom. If the slag is really large, robot has a lot of freedom for reaching from the position where it was at the beginning of the time interval to the position where it's at the end of the time interval. While where the slag is 0, which we will now look at, so if there is no slag, the robot has to really go on the monotone sequence. So really has to always go towards its destination on that interval, right? So if from this point to this point, robot got without any slag, it means that it was always moving either to the right or up. And the thing that we can now do is that we can bound a slag on, like we can bound a number of turns of a robot with no slag. And why is that? Let's have a blackboard now. So imagine that we have a robot that is doing a lot of turns, but has 0 slag on some interval. So as I said before, the reason we cannot flatten is because there is a different robot. Like reason where we cannot flatten neither of these cells is because there is a visible. Okay, red is not visible. Let's try yellow.
Yes.
Yellow is visible. Yeah. There is a different robot that would have a collision in here. But if this number of turns of that robot is a lot, then there is a different robot then there is one robot that also has a lot of collision, right? So there is another robot which still is doing a lot of turns, and every time it's kind of going at the same speed as the white robot, because white robot is not stopping all the time. It's moving. There's no slack. The yellow robot, to always force a collision if we flatten, the yellow robot also has to be always moving. So it has also no slack, which means that we found a different no slack robot that is doing a lot of turns. But the important thing is here that this one has to stay always below the white one. So yellow has to always stay below the white one, because if they would collide in here, then they would collide also if the yellow tried to cross. So there will be no, which means we can apply the same argument for the yellow one. We have only k robots, so we reach somewhere at the bottom a robot that we're still doing a lot of turns, but there's no one under, and such robot cannot exist. So also the wide at the beginning, right? Because it's turn minimal, so if he doesn't have anyone below that would block him, he's not doing more than one turn. And if we just split a robot that has some small slack into intervals without slack, then we can see that also a robot that has small slack has a small number of turns. Okay. Now, if we now have all robots that have small slack, then we would be fine, because now we know that small slack robots do small number of turns. We are happy. So we will have some robots that have some small slack and some that has very large slack that are allowed to waste time, kind of. And for division between what is small slack and what a large slack is, it seemed for us that it's much better for us to have like the gap between what the small is and what the large is to be very huge. And this is a quite nice trick. So what we can do is we kind of decide of what these jumps we would like to be. So we decide if we have one robot that is small slack and then everything else is large, we decide that small slack would be somewhere here, and a large slack would be somewhere here, and we say this is 1 and 2. So if there's just one before here and everyone else is later than this is just the real line, just a number line, then we say we have one small slack robot. If we have for 2, we define a next jump for 3, and we again say if we have 2 before this position and everyone else after position 3, then we have 2 with small slack and everyone else with large slack, and so on. And we have only k such positions, and each of them are kind of some function of k. Each of these jumps is some function of k and number of robots that we want at the small slack, and we have a huge multiplicative gap. So this gap is getting larger and larger by some multiplied by some function of k. So what we will always end up is that like we have some small slack, some large slack, and in case and there is a huge gap, so which we will need to work with. The other useful thing is that if we also have only large slack robots, so if all robots have slack at least some large function of k, then it's easy to just at the beginning move them apart to some positions such that each has its own unique row and unique column. Move them just by going straight, say first right and then up if they need to go right and up to the some again a position which is in some unique row and column for that robot, but it's close to their destination. And then use the remainder of this huge slack that we have to just brute force the final navigation to the destinations. So if we have only large slack, we are fine. And if we have only small slack, then we have small number of turns. So the only problem is kind of a combination of the two. And what actually, the combination is not even that bad. The combination is only bad if it's in the same interval. But if you have a robot that needs to go, that has no slack, so needs to go really far, and we have a different robot that has small slack, which means that distance between start and end is really small. Right, so if this was, let's say some blue robot like here, then on that, on the time interval, this blue robot might at some point walk together with the red one, but then it needs to turn and leave. So there will be like a really huge chunk of time where they are far apart. And so what we managed to show is that we can actually find a time interval where all large slug robots and all small slug robots are really far apart. And the reason for this is, right? So again, what we know, if we have a robot that has small slug needs to go really far, and a robot that has large slug needs to go close. They cannot stay together very long. And what we want some time interval where no pair of small slug and large slug are close to each other. And in that time interval, we can just deal with the large slug robots by ignoring the fact that by basically the same brute force that we have just for large slug robots with some additional fluff. So how we do that? So imagine that we have a robot that is doing lots of turns, right? This robot is doing lots of turns because if else all robots are doing small number of turns, then they are done, right? So we have a robot that is doing a lot of turns, and we want to, and imagine that now we have some large slug robot and small slug robot that are close to each other in some time interval. Because if we didn't have that, then we would have this nice split between large slug and small slug. So imagine that we have these two robots. So R prime is a robot that's doing a lot of turns on this interval from 0 to t. And we have these two robots. One has large slug and one has small slug that are moving close to each other. Now, it's somewhere in here. Now, this robot that is doing a lot of turns is doing at least one third of his turns either before this time interval where RR and RJ are together, or inside this time interval, or after this time interval. And we can, if it's before or after, so if it's before or after, then these two robots are always far apart. RI and RJ are always far apart. If it's in the middle, if it's at the same time, they are always close to each other, which now means that RJ, so the large slug robot becomes a small slug robot, and again, they are not anymore the pair of large slug and small slug that are close to each other. And because we had these huge jumps between what we consider what a large slug and small slug is, now we have a robot that become a small slug. It might be slightly larger than our previous bound on what a small slug means, but because we have one more small slug robot, the bound jumps much further, so we don't care about that. So RI and RJ will never cause this collision on either of these three subintervals we choose. We can repeat these k² times at most, and we reach the position where we have this situation that all large slug and small slug robots are always apart on that time interval, in which we can just reroute all the large slug robots to make less number of turns that already that one bad robot is doing there. So we decrease the number of turns, but it should not be impossible because we have been in the minimum turn solution. Okay, which means that kind of finishes the proof. So now we have only small number of turns. Because we have small number of turns, we also bound what you asked, the number of positions where they can stop. So we can kind of guess a roadmap and where of how robots move, and whenever they are kind of going through the same vertex or kind of or even in the same line, but especially through the same vertex, we always can guess which of the two is going first through that vertex, which makes us possible to write an ILP that exactly describes this roadmap with all our guesses and has only bounded number of variables. And we can just get it by Lenstra, the rest. Okay, so this kind of finishes the first result that I wanted to discuss. And the remaining results I will just mention more or less. I will not go into many details. So one more result about the makespan that we had, it was quite recent, is we also show that we can get FPT on actually only on these kind of trees. So on trees where every vertex has degree either at least 3 or 1, right? So we don't have vertices of degree 2. On these kind of trees, we only showed kind of additive approximation. And we kind of believe that what we did for these trees also works here, but with much more work. So, but the problem is hard even on these kind of trees. That kind of nearly straightforwardly follows from what you showed, that it just add one gadget to make it degree at least, like to remove all degree 2 vertices. Yeah. So what we showed is we gave approximation that has this running time, so FPT running time, and interestingly is additive, so it's opt plus order of k to the 5, and which probably can be made k to the 3 or k to the 4, but order of k to the 5 is what was easy to show. And we show FPT on these irreducible trees. So just to mention, sketch a little bit of an idea for this approximation. So what we kind of do, we adapt a conflict-based search, which is which is the algorithm that is kind of used a lot in practice. So conflict-based search, in general, what it's doing is you find shortest paths, and then if there is a collision, you just branch on which of the two agent is not allowed to be there at that time, to be at that vertex at that time, and recompute that agent, right? So we don't do exactly this, but the idea is kind of the same. The idea is we start by some greedy allocation, and then when they are collision, we either branch or we do some brute force and that brute force will add this additive approximation, right? So what we do, there are essentially, if we have trees, there are 2 types of collisions. One is we have a really long degree 2 path on which we just branch, we are on trees, so, and we start by a solution that is kind of really just going on the shortest path, with maybe one going away if we guess it needs to go away, but it's just going on the shortest path basically, which means that these 2 agents, they really need to pass this long path, both of them, because we are on the tree, there is a unique path, and we can guess which one passes it first, and we say to the other one to wait at the beginning of the path until the other one reaches that beginning. And that's the modification that we do in this branch for this collision. And this doesn't actually make opt worse, because one of them anyhow in opt passes first, right? So if our guess is correct, which of them passes first, then the other one has to wait. The other thing is that it happens near something what we call a haven. And the haven is something where reconfiguration can happen very easily just on the spot, and where you can just have a vertex, you can have a robot waiting for a long time. which basically means Haven is a vertex of degree 3. So it has like there are some, like it cannot be degree 3 very close to leaves, to only leaves, but to only very few leaves, but else is vertex of degree 3. And what happens is that on degree 3, especially this degree 3, and it has like on two sides at least k vertices, and here maybe one. Then if then whatever let's do the yellow again. Whatever vertices we have kind of on robots we have on this side and on this side, we can just by really moving everyone on one side, all robots on one side, then moving them back by kind of exploiting this one additional vertex in here. By moving back and forth, we can reorder them in an arbitrary order, right? So even if you imagine these are two paths, and I want them in some particular order, then I pick which needs to be the first. I move him in this vertex here, move everyone to the right, move this guy to the left. I pick who is the second, do the same. So in some O of k squared or something like that, I can just, or O of k squared, k cubed, I can all of them move in arbitrary order I want them around that degree 3 vertex. So if the collision is around that degree 3 vertex, I just use this additional small time that we have for approximation to just reorder correctly. Where we lose this approximation. And that's basically the whole algorithm for this. And the only thing is that because they're always kind of going towards their destination, the same robots will not be colliding many times. They will collide once in the middle of the path and then once near the endpoint of the path that's a Haven. And so the reconfiguration around Haven happens only k times or k squared or something like that. I don't remember. And then we also had a look a little bit about this other optimization, which is this energy, this total sum of distances. So sum of distances. We showed its FPT on grids by basically the same algorithm, basically the same argument. Because a lot of these getting rid of turns just works also for this, optimizing energy. Interestingly, we were able to show FPT by 3-bit plus k. Notice that for the other one, we only showed it on some strain or some restricted version of trees, parameterized by k. And we get the same FPT approximation, but we get that FPT approximation for general graphs, not only for trees. Which was quite useful. And with respect to energy, so if parameter is energy, it is now, you can actually brute force in XP time, because you just guess which agent moves to which neighbor. So now it's not NP hard for constant, but it's W hard parameterized in general graphs, but it's FPT on graphs of bounded local 3-bit. It's like planar graphs and many other graph classes. Yeah, and that's basically it. Just some future directions. We have this algorithm on grids, but even on subgrids, so even if we have some obstacles on our grid, we don't really know how to do that for either of the two minimization, so either of the two objectives. What is for makespan, FPT on k plus 3-bit, or even even like on trees, we kind of believe that we can do it, but it seems to be a bit technical. Can we kind of extend it? Can we extend the ideas from that additive approximation? That would be also quite interesting to lift at least to bounded tree width or to general graphs. And looking at the problem also on a plane with actual robots that are some shapes like discs, rectangles, and so on can be interesting. And might be interested to also see whether some of the ideas that we had would be useful for implementations, right? So implementing the algorithm fully will not give anything because the algorithms have terrible running times, but maybe there are good ideas for some people. Yeah. Okay. So that's it. Any questions?
No, it's
So I was wondering, so you have some algorithmic results, which is not so common in this group. So I was wondering, like, if you don't say like directly that this robot is now serving like moving something from here to there, but at the beginning you have some robots and you only have some requests, like there is something that needs to be moving from this spot to this spot. Could you use your algorithms to?
So for the, especially like these algorithms for energy, so all the results for energy works on something where we have some robots have a destination and some don't. So some are just serve as an obstacle. So I'm not sure, it might be slightly different. So they're not picking items. They already start with an item, but only some of them have an item that needs to deliver, and some of them are just in.
Yeah, I was just wondering, like, apparently for this warehouse, like at the beginning you have some robots and you have like this to be moved there.
Yeah. So this works, but parameterized by where k is total number of robots, and we have some results now recently where we also showed some results parameterized by just the robots that needs to move, and there it's also quite hard. I think the FPT we have there is for tree depth, so tree depth plus k, not just tree depth plus k, and it's also for energy only, and we have hardness by energy for one robot. So W1 hard parameterized by energy when one robot needs to deliver something. And of course, it was already known. MP hardness for just one robot was known because this is kind of a rush hour. So the rush hour puzzle. So it's if you have a cars, that cars can move this direction or this direction, and you want to get this one car from here to get out. So this is known MP hard problem, which is exactly this question in geometric setting where you have rectangles, and it has been studied also in graph settings where it was already known to be NP hard even there.
You can have even more fun. It would be like weird. You can just take the item, take it like three. Like this is good and take it apart, or validate another item, and this one will be when delivered by operations.
And
this problem is very hard. You are just making it hard.
I think
but
there's some paper where they do it where they do this question for some of distances on trees in polynomial time. I don't remember whether it was just one robot. I think it was even like for arbitrary number of robots on trees, but I don't know whether this generalizes anywhere beyond that. I mean, that's an open question whether it generalizes anywhere beyond that. And even on the trees, I'm not sure whether it was one robot. It might have been just on trees. On trees, one robot needs to reach destination. And for that, I think they have algorithms. And it's not clear even whether it would be FPT by number of robots on trees with the destination. Yeah, if I remember correctly, I might be mistaken.
If not, then let's take the speaker again.